Hey guys, it's Miss Johnson and I'm here to bring you our notes for section 12.1. We are kicking off chapter 12 today, which talks about chi-square. Chi-square is a different type of test that we're going to do for distributions. So we're going to talk about chi-square today. So the chi-square tests for goodness of fit. It says, here's what the Consumer Affairs Department of Mars Inc. says about the distribution of color of M&M's milk chocolate candies produced at its Hackettstown, New Jersey factory. So we're looking at a case of M&Ms in a bag. And what colors are they? And what should we expect for the distribution? So that's what our probability distribution looks like. It says Jerome's class wondered if the distribution of color in a large bag of M&Ms, milk chocolate candies, differed from the claimed distribution. Here are the data from a random sample of 60 candies from that bag. So you get the count of each color in that one particular bag. Okay. So what happens here with chi-square is what we're looking at categorical data and the probability distribution of that categorical data. So the reason it's categorical data is because your responses are categories: brown, red, yellow, green, orange, blue. So the responses or the data that you're collecting is based on different categories, not numbers. So that's why it's a little bit different than doing a z-test or a t-test, because we're not looking at a mean and we're not looking at a proportion. We're looking at categories and we're going to inspect the probability distribution of those categories. So this is what our standard probability distribution is for the categories of M&Ms from this plant. This is what our random sample gave us. Okay, so let's talk about what we can do with that data. So if we want to test this bag of M&Ms to see if it's drastically different from what we expect the probability distribution to look like, we have to write a null and alternative hypothesis for our data or for the situation. So the null is that the distribution of color in the large bag of M&M's chocolate candies is the same as the claimed distribution. The alternative is that the distribution of the large bag is not the same as the claimed distribution. So that's typically what you're going to see when you see a null and an alternative hypothesis for a chi-square test. You're looking at, is the probability distribution going to be the same or is it not going to be the same? You could also write this out in symbols. So what they have here is that the probability of brown is 0.125, probability of red 0.125, and so on and so forth down the line. That's your null. And then your alternative is what they'll say is at least two of the PIs are incorrect. So at least two of these probabilities of our categories would be wrong. If you have two that are wrong, they're saying that's enough for us to say we're going to have something different here. We have a different type of distribution. So it says where P of the colors, the true proportion of M&M chocolate candies in the large bag of colors. That's them naming the parameter there. So you'll start to notice that when we look at chi-square tests, we're looking at categorical data. We're not looking at numerical data anymore. However, the setup of a lot of this is the same as what we've been doing. We're still going to be naming a null and an alternative. We're still going to have to list the parameter. So all of that is still kind of true here. So one thing that they caution you on, it says don't state the alternative hypothesis in a way that suggests that all the proportions in the hypothesized distribution are wrong. So your alternative shouldn't say that every single one is incorrect. So like in this case, they said at least two of the probabilities are wrong. So let's talk about how we figure out what the expected counts should be. So you're going to be finding expected counts for all of these situations. So it says, how many candies of each color should Jerome's class expect to find in their sample of 60 candies? Well, the way you get your expected counts is by taking n times whatever that probability is. So if I take 60 times the 0.125, which is what I expect, I get 7.5. 60 times the 0.125 for red, 7.5. Same for yellow, same for green. Then 60 times the 0.25 for orange, you get 15. 60 times the 0.25 for blue, you get 15. If you add up all of your expected counts, you would find that they all add up to 60. Okay, so this is a probability distribution. We know that we should add the probabilities and get to 100%, which means if we add the expected values or the expected counts, we should get to the n. All right, so let's take a look at just another comparison. So the observed is what they saw in the bag. The red bars are the expected. So you can compare the two and see how different they are. Brown looks pretty different. You got 12, you expected 7.5. Red, pretty different. You got 3, you expected 7.5. Yellow is pretty similar. This yellow one right here, 7 and 7.5. Green, I would say green's not even really that different. They're pretty close, but they're still different. Orange, very different. You got, 9? You got 9, you expected 15. Blue, you got 20, you expected 15. So it says, how likely is it that differences this large or larger would occur just by chance in random samples of 60 from the population distribution claimed? So in order to test that, how likely... Okay, that's where we're going to find that p-value when we would do tests and we find a p-value. We have to use a chi-square test statistic. Okay, so the statistic we use to make the comparison is called a chi-square. Chi is how you say that. And the Greek letter chi looks like an X. The X has kind of a squirrely piece to it, but that's read chi. All right, so here is how we get our chi-square test statistic. The chi-square test statistic comes from the sum of the observed count minus the expected count squared divided by the expected count. So for the M&M example, we'd have 12 minus 7.5. This was for brown, divided by 7.5. Then red was 3 minus 7.5 divided by 7.5. And notice they're squaring all those in the numerator. Then it was, I think this was yellow. 7 minus 7.5, this one was maybe green, and then it was, I forget the colors, orange and blue. So you can see that they're adding up each piece down the line where they subtract the data minus the expected. They're going to square that and then divide it by the expected. You get these 6 individual values, and when you add them all up, you get your chi-square amount. Okay, so the chi-square here is 9.8. Then you can use that to find your p-value. So this chi-square is going to be useful for us. This is the same thing as when we would find our z-star with proportions or our t-star with means. We'd find the z-star and find the probability, then we'd find the t-star for means in probability. Now we're doing chi-square for categories. Okay, some people remember it that way. Chi categories. You've got 2 C's that are starting you off there. So let's take a look at a different example. It says Carrie made a 6-sided die in her ceramics class and rolled it 90 times to test if each side was equally likely to show up. The table summarizes the outcomes of her 90 rolls. So she's got 6 sides, 5, 6, there it is. And she got a 1, 12 times, 2, 28 times, 3, 12 times, 4, 13, 5, 10, 6, 15. When you add them all up, you get a total of 90. Okay, so let's talk about what we should expect to see from Carrie's die, the die that she made. So in part A, it says state the hypothesis that Carrie should test. So the null would be that the sides of Carrie's die are equally likely to show up. Then the alternative would be that they're not. The sides of Carrie's die are not equally likely to show up. Oops, likely. I forgot the word likely in there. Sorry. To show up. Okay. So that's our null and that's our alternative. You can see that there's not a whole lot of change between the two. The null says that the die are, so they should be equally likely. You should get this around the same, if not exactly the same result for each outcome, the outcomes 1 through 6. Then the alternative is that they are not. Now, you can take a look at the results, 12, 28, 12, 13, 10, 15. You can very clearly see that those are not the same. Okay, you don't get an equal number of rolls for each outcome. So therein lies the reason to test. What's the probability that this happens? How likely is it? Should we call this a strange, unique situation, or is something up with Carrie's die that something is wrong? Okay. All right, so let's take a look at part B. In part B, it says calculate the expected value for each possible outcome. So the expected value, if the null is true, the expected value of each outcome is the same. Okay, and that expected outcome would be 90, because that's how many times she rolled it, times 1/6, because there are 6 possible equally likely outcomes. So 90 times 1/6, which is 15 for each side of the die. Okay, and then you can even go one step further and you can make a table of this. Outcome, and then the expected count. So outcomes are 1, 2, 3, 4, 5, and 6. Expected account for every one of them would be the same, because theoretically, the probability of rolling each side of the die should be the same. So that gives you a total of 90 rolls if you added all those down. Now let's take a look at part C. So now we're going to actually go in and calculate the chi-square value. So this is the test statistic for this particular test. So in part C, my chi-squared would look like this. I'd have 12 minus 15 squared over 15 plus 28 minus 15 squared over 15 plus, and all the way down, 12 minus 15 squared over 15 plus 13 minus 15 squared over 15 plus 10 minus 15 squared over 15, and one more, I ran out of room, sorry, 15 minus 15 squared, that's a minus sign, over 15. Okay, when I do all of that, you can type all those into your calculator, but here's the 6 values that you get. You get 0.6 plus 11.27 plus 0.6 plus 0.27 plus 1.67 plus 0. And then putting those all together, I get 14.41. So that's my chi-squared value, okay? Part of why we subtract and then square them and then divide by the 15, part of why this is called chi-square is because we have to square the numerator, because we need to end up at all positive results there. And the only way to end up at all positive results is to take it to an even power. So that's part of why this is called chi-squared, is because we're going to end up with all positive results here. All right, so that's just a very brief introduction of our chapter 12 lesson. So this is section 12.1. We're going to pick this up with the second video and actually go through some of these chi-square tests and talk about the probability part of it. So thanks for tuning in, and I'll catch you next time.